Hello and welcome back. In this video we'll be looking at what is known as the difference quotient. And the difference quotient is what we will use to look at the slope of various graphs. And sort of in the past we've talked about the slope of straight lines. And what we meant by slope is sort of the rate at which the graph is increasing or decreasing. So slope is going to be a rate, and it's going to be how fast the slope is, how fast the function is changing over time. So, for instance, if we look at the straight line, and we want to look at the slope, well, we know that the slope is going to be 1 divided by 2 because we're used to lines being expressed as mx plus b, where m is going to be the slope here. But when we look at the line, when we look at the graph of the line, we can see that the graph is going up as we move to the right. And how fast is it going up? Well, for every 2 that we go over, we're going up 1. So if we think about the slope being the difference in the height divided by the difference of how far we've gone over. If we go up 1, we've gone over 2. So, and it doesn't matter where we do this. If we look at, from x is equal to 2 over to x is equal to 4, again, if we go over 2, we've gone up 1. So that rise over run is always just 1 over 2. If we're over here at -4 going over to -2, we go up 1 and over 2. It doesn't matter where along our line we are, it's always up 1 over 2. If we were to look at a graph like this, on the other hand, where we have fx equal to x squared, we've got this nice parabola. And we can see that, for instance, over here we're coming down, but when we cross 0, we're going up. So the slope is changing, and depending on how we want to calculate the slope, we might get some sorts of different answers. So for instance, if I want to calculate the slope, say right here as x is equal to 1, well, if I go over 1, I've gone up 3. So is the slope here going to be 3? Or if I look backwards, and if I go over 1, I've gone up 1. So is the slope 1? Is the slope actually somewhere in between there? How do we calculate the slope right at a particular point? And one thing I want to do is I want to emphasize the definition of slope being we're just going to take the difference in the height divided by the difference in how far across we've gone. So over here, when we're looking at this point, I need to take, if I want to take the slope, I have to look at the difference in the height divided by the difference in how far we've gone over. But if I want to find the slope exactly at that point, I don't want to go too far over. So for instance, if I come over here, and if I'm looking at the slope between when x is 1 and when x is negative, when x is -2, this point seems a little bit too far away, and the slope between them would be going down. So I don't. That's essentially just too far away. What I want to do, what I would really like to do, is take this point and take a point really, really close to it and look at the slope there. So this is going to be our strategy. We want to find the slope between 2 points that are very, very close. So what I'm going to do is I'm going to start extrapolating here. If I'm taking the difference in the height, which is y1 minus y2, over the distance in the x values, x2 minus x1, what is y2? Y2 is the height of a function. So y2 is just going to be what I get if I plug x2 into my function. Also, y1 is just going to be when I plug x1 into my function. So I've got the difference between two function values. Next, what I really want to think about is if I were to express, if I want to find the slope right here at this point, I want to take a point really, really close to it. So here's my strategy. If I'm at the point x, something really close to x, really close to x, is going to be x plus a little bit. My old math teacher referred to this as x plus a hair. So this is why we'll use the letter h here. What we're going to do is we're going to take x and we're going to go over just a little bit, just a little bit to the right. So we're just going to take x plus a little hair, so that we're over just a little bit. So x2 in this instance is going to be x scooted over by a little bit. And x1 is just going to be our original point. So here we're at our, x is our original point, and we scooted it over just a little bit. And then we'll take x plus h minus x on bottom, and you'll notice that this will simplify. The x's will cancel out. This right here is what we will call our difference quotient. So this is going to be the height of the function at x plus a little bit minus the original height of the function all over all over h, which is the same thing as x plus h minus x. Notice that this is a slope. So again, this is the height of a function. So this is y2 minus y1 over x2 minus x1. But the x2 minus x1, the x's will cancel and we're just left with h. There is one final caveat. We always want to simplify this so that h may approach 0. Essentially, what we want to do is we want to consider what happens when h is very small. As in, if we're trying to find the difference, or if we're trying to find a slope, we want to get these 2 points as close as possible. So that our slope is going to be more accurate. So what we'll end up doing is we want to take the limit as h approaches 0. But let's first just do a couple of examples. Let's find the difference quotient of f of x is equal to x squared. So the one that we were just looking at. Well, the difference quotient is going to be f of x plus h minus f of x over h. So let's start simplifying this. F of x plus h. So let's plug x plus h into here, and I'll get x plus h squared minus f of x. F of x is just x squared all over h. And we can simplify this. X plus h quantity squared, so x plus h times x plus h. This is going to be x squared plus 2 times xh plus h squared minus x squared all over h. So thus far, what have I done? I've just plugged in x plus h into my function. Okay, so that was the first step. Next, I had to simplify that a little bit, and what you'll notice is that I've got a plus x squared and a minus x squared. So these guys are going to cancel. So what am I left with on top? 2xh plus h squared divided by h. Oh, and what happens when I'm dividing by h? And h will cancel on the top and bottom. So what I'm left with is 2x plus h. And that's the difference quotient. That's the difference quotient for x squared. It's not too bad. We just have a formula for it. And again, this formula is just the slope. Let's find the difference quotient for x cubed plus 4x. So again, the difference quotient, we want to plug in x plus h, x plus a hair, and we'll look at the difference, we'll look at the rise of our function, how far it went up, versus how far we went over, just a hair. So I need to plug x plus h into this function. So if I plug x plus h into here, I'm going to get x plus h cubed. And if I plug x plus h into there, I'm going to get 4 times x plus h. And then I want to subtract the original function, so I want to subtract all that. So we're going to subtract x cubed and the 4x, and we're going to divide everything by h. So here's where we'll have to do quite a bit of simplification. If I were to try to just let this, so one thing I could do right away is just say, oh, I'm done, right? Well, this technically isn't simplified. If I were to try to let h go to 0 here, I can't divide by 0, can I? So I don't really want this h on this bottom of the fraction. So I'm going to try to simplify this as much as I can to cancel out the h. So what is x plus h cubed? And again, this is going to be x plus h times x plus h times x plus h. This is something that I could do over here in Scratchwork. Or there's a handy trick involving Pascal's triangle. If you're interested, I can talk about this more, but here is x plus h cubed. And then I take 4 times x plus h, so this is going to be 4x minus 4h minus x cubed minus 4x. Why did I write minus there? This should be a plus. Plus 4x plus 4 times h all over h. And what you'll notice is that I have an x cubed and a minus x cubed. And I have a 4x and a minus 4x. So all those guys are going to disappear. And in one fell swoop, I'm dividing everything by h, right? So I have 3x squared h. That's just going to be 3x squared. I have 3xh squared divided by h is going to be 3xh. I've also got an h cubed divided by h. Well, that's going to be h squared. And I've got a 4h over here divided by h. That's just going to be 4. And oh look, this is something where I can let h go to 0, and that would be an easy limit to take. So again, after we simplified our difference quotient, we got this. Let's do one more example, and this will be a somewhat tricky example just because it has some fractions in it, but we'll manage. So our difference quotient is going to be we'll plug in x plus h, and we'll subtract f of x, divide everything by h. Again, we have rise, so how far did we go up if we go over a hair versus how far did we go over just a hair. So f of x plus h, we can plug x plus h into our function, minus f of x all over h. What I'm going to do, in fact, is I'm just going to simplify this top for a second, and then I'll divide everything by h. So let's just look at the top of this fraction. I have two fractions that I'm subtracting, so I need them to be over the same common denominator. So what I'll do is I'll take the left fraction and I'll multiply everything by x. So if I multiply the top and bottom by x, notice that this fraction and this fraction are the same. And I want to subtract the second fraction, but I need the same common denominator, so I'll multiply everything by x plus h. Okay, so this is just my scratch work off to the side. When I subtract this, I'll get 2x minus, and then let's simplify this. This is going to be 2x minus 2h all over x times x plus h. And the 2x's are going to cancel, so I'm just left with minus 2h. So this is the top of the fraction. This is going to be minus 2h over x times x plus h, all divided by h. Okay, let's simplify this. If I'm dividing a fraction by h, it just shows up on the bottom of the fraction. So far, I just divided this by h, and we'll see that those cancel, and we're left with minus 2 over x times x plus h. A lot of work, but this is only algebra. There's nothing else going on.